Hello everyone, my name is Vinicius Gomes and I'm an application engineer here at Altair, and today I will show you how we can perform a Squeak and Rattle assessment with Altair SimSolid. I have divided this video in 4 main topics. First, I will do a high-level overview of Squeak and Rattle problems and how we address it with CAE. After that, I will briefly talk about SimSolid, if you have never heard about this Altair tool. Then we will prepare a model from scratch and extract the Squeak and Rattle results using SimSolid. And at the end, we will have a few conclusions about the whole process. All right, so I think you already know it, or at least have an idea of what it is. But the squeaks and rattles are all of those unwanted noises that the vehicle produces under a certain load. Usually when we are driving it, of course. The rattle is caused by the impact between 2 different components, and the squeak is caused by the friction between them. And all these issues, they are directly related to the perceived quality of a product. And especially today, with electric drive lines and quieter vehicles, they can be very easy identified by the customer. And I have here 2 different audios to represent each one of these problems. This first one would be the rattle. So here we can hear the impact between 2 different components. And now the second one is the squeak. All right, which is caused by the friction between 2 different components. And with Altair, we have a simulation-driven approach to identify and eliminate these issues. With simulation, we can identify such issues at very early stages of development, reducing the need of prototypes and testing, and delivering a way more robust solution instead of relying on what we call the quick fixes, such as foams and tapes, of course. Since we are tackling these problems at this very early stage in the design cycle, we can propose different designs instead of relying on those quick fixes that I mentioned. And in the background of our tool, we are running a methodology called the E-line method. And this methodology was first published in 2 SAE papers, one from 2010 and the other one from 2012. And after that, after the methodology was proved and validated, we brought these into our portfolio in an automated way. And how exactly does it work? The E-line method with SimSolid is based basically on 2 main inputs. The first one, of course, is the CAD model, and the second one would be an excitation. This excitation can be a test data, shaker load, PSD, sine sweep. So any kind of dynamic load, we can use it here. And the main difference between this method and a physical test, for example, is that here we are not measuring noise exactly as we would do in a physical test, for example. In short terms, what we are doing here is creating virtual transducers along the interface of 2 different components and tracking the relative displacement between them. So once I know what is the actual gap between 2 parts, I will compare this gap with the relative movement. And if the relative displacement is bigger than the gap that I have, it means that the parts will get in contact and generate noise. This is the basic idea here of the whole methodology. And it's something that we can see here in this short video once again. So we can hear very clearly the noise that this plate creates once we have the impact with this other region here. So that's the idea in the background of the tool. Comparing the relative displacement of them with the actual gap and understand if there is a risk or not in that particular region. Now I'd like to briefly introduce SimSolid in case you have never heard about it. SimSolid is a structural simulation tool that operates directly on the original and unsimplified CAD geometry. This tool uses a completely meshless method with this unique adaptive solution, where the problem will be solved in a number of passes in order to achieve the solution convergence. And this method gives SimSolid both the speed and the accuracy. So we can run analysis in seconds to minutes. It runs very, very fast, and the results are very good. This is a truly game changer in the structural simulation domain, and we have lots of comparisons against the finite element method, which is the traditional method that we use in other CAE tools. And these tests, they have been made internally and by our customers themselves that proves SimSolid's accuracy and value. I will add here a few links in the description of this video for your reference. So we have a lot of success cases that we worked with different customers across different industries, and then you can check for your reference, okay? And the key point here is that SimSolid eliminates two of the most time-consuming tasks of the finite element method, which is the geometry simplification and meshing. And apart from that, SimSolid also automatically creates contacts and identifies other connection types like bolts and welds, for example. So we are saving a lot of time during pre-processing, and we can do a lot of more loops and design iterations for a particular model. And this allows us to perform the Squeak and Rattle assessment very fast. And with this, we can evaluate and compare multiple designs, as I just said, so we can do this A to B comparison and understand how I can reach to an optimal final model. And this one is the one that will move on into a final validation, for example, with the traditional FEE method, instead of do this back and forth process. So I do the analysis, the FE analysis, it's not good, I go back to the CAD, improve the CAD, then I go again, generate a new mesh of this new product, and so on. So I can do a lot of iteration directly in the CAD, and then the model that goes to the next stage, the FE validation, it's a way more robust design, all right? So no more talking, let's go to the tool and see how exactly we can perform this Squeak and Rattle assessment using Altair SimSolid. All right, so here we are inside SimSolid. The first step here will be, of course, to import the CAD. So I will bring here the raw CAD, and we will build this model from scratch. So as soon as we import the model inside SimSolid, I already have this option to define connections automatically. And these connections will be based on a certain gap distance and also a certain penetration. Here, I can keep these values as default. For each model that we have, SimSolid automatically calculates this, and I can do OK. And then here in the project tree, we can see that I have already the option connections, and all of them will be here already created. Here we can double check. So by default, all the connections, they are the bonded type. If you double click, you can edit, you can modify it if you need. But in this case, I just keep it as it is. I want a bonded connection. I just want to review and make sure that everything is in place. So here for this model, you see it's a simple air vent model. All the connections that I want are related to this pin here. So I want to connect here the blue component to the pink one and the same on the other side. And here I can navigate through the connections and I can see these red dots representing the connection points. And here, since I'm interested about the relative displacement between each one of these interfaces around the air vent, I'm not really interested about this type of connection, because if I have set a bonded contact here in this region, it means that I have zero relative movement here, which is not what I'm looking for. Here I'm looking for the real relative movement, and then I will compare the relative movement with the actual gap that I have there. So I want to make sure that I don't have these type of connections around the model. So this guy, I can delete it, and then I'll just look around the model again. So here, another one that I don't need it. I will delete once again. Let's check the others. 5, 6, 7, we are good. Now on the other side, there we go, another one that we don't want right here. And another one here on the top. The others seem to be fine. So if I select all of them, we can see I have mainly 4 areas of connection. Very good. In terms of material, I already have a default material here defined. So since this is a IP plastic part, I'm defining all of them as a simple ABS plastic from SimSolid material library. Of course, if you have your own materials with your own properties, you can add them here. But for this demonstration, I will simply select one of the library. Okay? So this will be the default for all the components here. All right, so once my model is in place in terms of connections and materials, I can start to prepare the studies that I'd like to do. And here, to obtain the Squeak and Rattle results, we need 3 main steps. The first one will be a modal analysis. So we want to extract the modes, the vibration modes of this structure. As a second step, these modes will be used to link to a transient analysis, so a time domain simulation. And with the time domain simulation, then we can calculate the Squeak and Rattle results. So there are 3 basic steps. You see how easy it is to prepare the model. So the first step, as I mentioned, we need to run a modal analysis. So right here, I have the modal option. And it's very easy to set up. I basically need to specify the number of modes I'd like to calculate. Let's say 20 modes. And I need to provide the constraints or the fixation points of this structure. Here in this vertical toolbar, I have all these options. So if I want a movable support, if I want slider support, so all of them are here. We go with the immovable one, and we will fix the model here in this area, in all the 4 ones around the model. Here and here. There we go. So I already have everything here, number of modes, constraints. Now I can simply run. Here, yes, I want to use the default materials. And now all I have to do is to wait a little bit. You see that the SimSolid is calculating the solution for us. And here we go, we already have the results. So if I right click here and say information, the analysis ran in 15 seconds. So as I said, this is really fast. And one of the major advantages of using SimSolid. And here you can already check the modes. So we have the first one at 96 Hertz roughly, the second one in 117 and so on. So we have all the 20 modes that I requested right here. Good. So next step, once I have the modal analysis in place, I need to create the transient solution. Transient solution will be here under this second option, so transient. And as I mentioned, we need to link the transient dynamics setup to a model analysis, which in this case I already have it here. Now, in terms of time span, I want to define for how long this transient analysis will run. Here, I will import a signal that I have, and the signal has 4 seconds. So I will set here to 4 seconds. And the second thing that we need to define here is the damping. So damping is something very important here when we are talking about dynamic analysis. And a traditional value that we usually take is 3% damping, which is what we have defined here. If you do not have any kind of test data to compare or anything like this, 3% is a good value to start with. But then once you start to have this type of data, then of course you can tune this in order to achieve a better correlation. Okay. All right, so the next step, I need to import the signal that I want to apply to this model. I do it through, again, this vertical toolbar. Here I can import the CSV, and I have here the signal. If I open this guy in the text file, you'll see that this is nothing but the time in x-axis and the amplitude in y-axis. So I can open it, and there we go. I can check the signal. Everything looks fine. 4 seconds duration, okay. And now I need to define where exactly I will apply the signal. It's okay, here we have the fixation, but maybe eventually I want to apply it here at the center of the structure. You can do it. But in this case, I will use the fixations to apply this excitation. So this is what we call a base excitation, where all the fixations will be receiving this excitation and will vibrate together. And this option is right here. So you can see we have base excitation. And all I have to do here is to select the constraint, so immovable one, that we created in the model solution. And down here, I will select the excitation type. It's I want to apply an enforced displacement in terms of millimeters. My amplitude will be 1. So when I set this amplitude, basically what I'm doing is adding a scale factor or a multiplier for the time function that I have here. In this case, let's go with unitary amplitude, but not in the x direction. I want this amplitude in the z direction. Imagine here that this will be installed in the vehicle, and probably the strongest vibration comes through the z direction, right, from the road. So 1 in z and OK, and there we go. I have already the simulation in place, and I can solve it. Cool. Once again, the model is already solved. If we check here the information, this took 19 seconds to run. So far I have 15 seconds for the model analysis and 20 seconds for the transient solution. So not even 1 minute yet of solution run. And let's just check the results a little bit, see if everything looks familiar and I don't have any kind of strange results. There we go. So the maximum displacement that I have, it's 3 millimeters around this region. So it's something that it's reasonable. If you want to animate, you can see how the model behaves. Here, of course, there is a scale factor applied. We can check it here. So we see there is a 12.6 scale factor applied here. And now the final step, that is exactly what we are looking for. It's the Squeak and Rattle evaluation. Here, again, under the same dynamic load cases, I have here the option Squeak and Rattle. Once I click here, the Squeak and Rattle setup needs to be associated to a transient analysis, which is this one. And here I need to define what we call the gap tolerance and also the tolerance for the squeak evaluation. How does it work? So this tolerance, it's the variation that your default gap value might have. So usually you have, for example, the gap 1 millimeter plus minus 0.5, or 1.5 millimeters plus minus 0.8. So this is the tolerance that we are using here as a reference. When we are post-processing the results, I think that things will be a little bit more clear. But for now, I can just confirm. And now I need to create what we call the sampling points, which are the transducers that I mentioned earlier that will be responsible for tracking the relative displacement. And here, to create this sampling point, I have a few different options. So I can do a group connect, edge to surface, face to surface. But here, I think this one is the most suitable one, at least for this model. I choose a primary part, which is the main component here. And the secondary part will be the other two. So I can select both of them here. And here I will define a certain gap and penetration tolerances. Here, this is important to mention that this is nothing related to the Squeak and Rattle evaluation itself. This is more like a search distance for the creation of these sampling points. So once I define the gap as 5, everything that is under 5 millimeters between the primary part and the secondary parts will be, sampling points will be created. So if I do find here, you see that I have many different sampling points here in this list now, and I can check. So all of these red dots, they are the sampling points and the transducers that I said that will be responsible for tracking the relative displacement between the parts. So here, I want this guy, sampling point 1, looks good. These others, I'm not sure if I'm very interested about them, so I can delete, let's see, because number 1 seems to already capture most of the area. You see all around the air vent. And the same here for number 8 on the other side. So the others here, I can basically delete them. I am not really interested about these regions. And this gives me 2 sampling points, just as I wish. Okay. And this is it. Basically, you see very fast, I just need to define these sampling points, the areas that I want to calculate for Squeak and Rattle, and now I can hit the run button again. And there we go. Now we have the results, and let's take a look at them. Here, when we are looking at the Squeak and Rattle results, here, at least the first plot, it's something more straightforward. So we can see here that the green dots, they represent not a risk, neither for Rattle or Squeak. The blue dots that we have, they are risk for Rattle, and here it's not the case, but if we had any kind of red dots here, then it would be for both. So there's a risk for Squeak and for Rattle. And once we plot the results, we can check different response types. The first one is this one, the final status. The second one would be the initial gap. So you can understand what is the actual gap that we have here. So based on this legend, for example, here would be something around 1 millimeter or 1.2. Here on the right-hand side, it's something around 0.6, 0.5, for example. So here is the initial gap before I apply the excitation that I have. The third option would be the minimum gap. This one, it's for the Rattle evaluation. So once I select this, I can see what is the actual minimum gap here. And more than that, with this option, the minimum gap, I can click on one of these response points, for example, this guy, and I can see how it looks like through the time response. So I have the relative displacement in the time response. So if you remember, when we prepared the model here in the setup, I defined 0.5 millimeters as the threshold. So when I plot the chart, you see that I have this red line here right at 0.5 millimeters. And this is how we use to define a certain point as a rattle risk or no risk. Here I have the relative displacement between the two parts here in the interface, and as soon as the line crosses the threshold of 0.5 millimeters, this will be a risk. So the relative displacement here starts at the initial gap. So if you remember here on this side, the initial gap was around 0.6, 0.5, so the actual value here is 0.52. So here's the initial gap, and then the relative displacement here eventually ends up crossing this limit of 0.5, which means that the gap will be closed and I will have the contact between the parts, which means that this is a rattle risk. If I check for another area, for example, I think here it was a safe area. Let me check. Yeah, it's green. So if again I plot the minimal gap for this guy, you see that I'm very far from 0.5. So if I set this guy here to let's say 0.45, there we go. So here is my threshold and I'm very far from it. And on the squeak side, it's the final one, so the maximum tangential displacement. Here we can check the same plot, but now for the squeak, if you remember, we are not looking at the gap direction, but we have a certain plane here that the squeak can happen because it's the friction between the structure. So if I check one of those, probably we will not find any issue here, but here, since I have a plane displacement, it does not go up and down. It's more like an absolute value, but I don't have any point here that goes above 0.5 millimeters. So here, if I set, for example, 0.55, there we go. Here I have the threshold. So this point should be above this limit of 0.5 in order to have a squeak occurrence. Okay, just as a reference for you. So as a conclusion, we could see that SimSolid is very fast and able to predict this type of squeak and rattle problems. The pre-processing, which is the task that most take time during the traditional FEA process, here it's one of the major benefits inside SimSolid. We were able to go from importing the CAD into final results in less than 20 minutes, and of course with my explanations and all. So if I simply do it in one shot, probably it would take 10 minutes or less. So this is very nice and can be used to do all of these design iterations and understand what is the behavior of your component as soon as you have the CAD available. And of course, these results, they can be used as a reference for the FE validation in the future. And as a screening, let's say, for when we reach this level, we can reduce the areas and the points that we want to evaluate. So I can do this screening here in the CAD, and then when I jump into the FE validation, I will create less sampling points and less areas that I need to evaluate, because I know that certain areas are already safe. I am only worried in certain critical points. Okay? So I hope this was useful, and thanks for your time. See you in the next video. Bye bye.